Okay. And according to the chain rule, du by dt. This is del u by del x, dx by dt plus del u by del y, dy by dt. Del u by del y, dy by dt. My question the bra. Okay, this is okay. See, where u is a function of x and y, and x and y are functions of t. See, last time we discussed this. If last time discussed if u is a function of many variables, x1, x2, and so on till xn. If u is a function of many variables which are named x1, x2, x3, and so on till xn, and each of this x, let us say xi, is a function of t, I from 1 to n. See already du by dt du by dt say del u1 by del u by del x1 dx1 by dt plus del u by del x2 dx2 by dt, and so on till del u by del xn dxn by dt. Sigi special case as a special case of this, we considered what happens if y is a function of x. So for example, the special case I'm going to discuss u is a function of x and y, and then y is a function of x. Sigi case what will be du by dx, du by dx. From this particular expression, we get du by dx equal to del u by del x plus del u by del y dy by dx. See how last time we obtained up to this expression. Now let us suppose another case, which is u is a function of two variables x and y, and then x is again a function of two variables s and t, and y is also a function of two variables s and t. If this is the case, what will be del u by del s? Sigi case del u by del s kari what will be del u by del s? This will be equal to del u by del x by del s. Here s is a function of two variables s and t. We are differentiating x partially with respect to s. Plus plus del u by del y by del s. Now if I want to differentiate u with respect to t. We have del u by del x by del t plus del u by del y by del t. Okay. Let us calculate. Let us calculate let us consider one example. Example I could discuss our see example say let me start on a new page. Let us consider one example. This is the Laplacian operator. Laplacian operator have the second partial derivative with respect to x plus second partial derivative with respect to y. So you see del 2 by del x square plus del 2 by del y square. This is the Laplacian operator in 2 dimensions in x and y. Data, the Laplacian operator is expressed in terms of Cartesian coordinates. Although we can also express this Laplacian operator in polar coordinates. The Laplacian operator is polar coordinates expressed. And so what is the relation between Cartesian coordinates and polar coordinates in 2 dimensions? The relation is very simple. X equal to r cos theta, y equal to r sin theta. Let us take a special case. Case now, constant r, where r has a constant value. This is a constant. Constant r example and let us express this Laplacian operator in terms of theta. Let us express the Laplacian operator in terms of theta. First, let the Laplacian operator this operate on a function f xy. F is a function of x and y. Functions let us operate the Laplacian operator on this function. Then we have Laplacian operating on f of xy. This is equal to del 2f by del x square plus del 2f by del y square. Then this Sigi expressions now let us express del f by del x in terms of theta. So del f by del x at constant value of y. This is calculated at constant value of y. This is equal to del f by del theta by del x. This is calculated at constant value of r, and this is calculated at constant value of y. X and y are functions of r and theta. This also means r and theta can also be expressed as functions of x and y. Maniko, r and theta can also be expressed as functions of x and y. So for example, from this we get r equal to root over x square plus y square, aduga theta equal to tan inverse y by x pangel. From this expression we get r equal to root over x square plus y square and theta equal to tan inverse y by x. So here we have partially differentiated f with respect to x. This can be expressed as del f by del theta by del x. Now let us expand this. F is a function of x and y, and then x and y are functions of r and theta. This means f is also a function of r and theta. So f can be differentiated with respect to theta. So let us calculate del theta by del x. So del theta by del x at constant value of y. What is theta? Theta is tan inverse y by x. So this is nothing but del by del x of tan inverse y by x. And this should be calculated at the constant value of y. So what is this? This is nothing but 1 divided by 1 plus y square by x square, and then we differentiate y by x with respect to x again. With respect to x again, and this will give you minus y by x square. So this is equal to this is equal to this minus so y later. So the x square later, this is x square plus y square. And this is equal to now what is y? Y is r sine theta. R sine theta. And when we take r as a constant, this becomes y equal to a sine theta. So this is minus a sine theta. This is minus a sine theta. Y is minus a, sorry, minus y is minus a sine theta. And what is x square plus y square? From this expression we get x square plus y square equal to r square. We can also see it from here, x square plus y square equal to r square. And for when r is constant, when r is equal to a, this denominator becomes a square. So this is finally equal to minus sine theta divided by a. There you go. So we have calculated the value of this del theta by del x constant y. So now we can substitute this value in this expression. And we get del f by del x at constant y is equal to del f by del theta at constant r multiplied by this, and this is nothing but this. So this is minus sine theta by a. We want to calculate the second order partial derivative. We want to calculate this, the second order partial derivative. We have calculated the first order partial derivative. So let us differentiate this again with respect to x. Del 2f by del x square. This is again nothing but del by del x, del f by del x at y. This means you differentiate f 2 times with respect to x. Now this differentiation with respect to x, it can be expressed as differentiation with respect to theta, del by del theta, del f by del x at constant y, del theta by del x at constant y. Sidi aning breo. Sida tau hisiga mani. Del f by del x is nothing but del f by del theta times del theta by del x never. So it is this del by del x of this function is nothing but this function with respect to theta differentiate tau, then you differentiate theta with respect to x tau. Yarba. Then after this, Sigi kari ka manarani. I will say that this is equal to. Now say the mamang the hot kibuta del theta by del y. Del theta by del y is given by this expression. So this del theta by del x. Del theta by del x is given by minus sine theta by a. So this del theta by del x, it should be equal to minus sine theta by a. So this is minus sine theta by a. Del theta by del x we have calculated earlier, and this value was minus sine theta by a. Yarba. Then this is del by del theta. Del by del theta, and this is minus sine theta by a del f by del theta. Ya veo. Del f by del x del f by del x is minus del f by del theta sine theta by a. This del f by del x, this term substituted this term. Del f by del x is nothing but minus del f by del theta sine theta by a. Aduna sigi value is money among the hot carbon. So we are simply substituting this value here. And del theta by del x is this minus sine theta by a. This is this value. And this is equal to this value. Now let us differentiate this. Minus sine theta by a. This is a product of two functions. This is a function of theta. This is again a function of theta. So let us apply the chain rule. Sorry, product rule. So first let us differentiate this. Sine theta ki differentiation kai now. So minus cos theta by a. So first you differentiate this and you keep this as constant. Minus, now you keep this constant and differentiate this. This is del 2f by del theta square. So this is a function of theta. This is also a function of theta. and you are differentiating with respect to theta, so we have used the chain rule here. Chain rule, sorry, chain rule, not we have used the product rule here. So now you multiply this, what do you get? Minus minus plus sine theta cos theta divided by a square del f by del theta. So this minus and this minus plus sine theta, what do you get? Sine square theta. Sine square theta by a square del 2f by del theta square. So aku hojik phangisi kari no del 2f by del x square je siga mane yen phangbane. Hojik kari hoto wali. Now we need to calculate del 2f by del y square. Sigisi mu hoto wali sigisi samjhalage. You can calculate this expression by using the same method as we did earlier. Cos square theta divided by a square del 2f by del theta square minus sine theta cos theta divided by a square del f by del theta phangnew. So is going to solve the one. Aduna habidi kaino sigi anijit tijanaro. Now you add this and this anijit tijanaro. Adri left hand side anijit tijanari, right hand side anijit tijanari ko adri ai kari phange. So del 2f by del x square plus del 2f by del y square equal to kari phangage ngo saida sigiziga cancel tawnabra tamadabra ngo tijanabada. They will cancel out. Natra. So what remains is cos square theta by a square del 2f by del theta square plus sine square theta by a square del 2f by del theta square. So the I carry common low 1 by a square del 2f by del theta square common low. So this is 1 by a square del 2f by del theta square common low I carry phange cos square theta plus sine square theta. Cos square theta plus sine square theta dikano. This is 1. So this is equal to 1 by a square del 2f by del theta square. So del 2f by del x square plus del 2f by del y square is equal to 1 by a square del 2f by del theta square. So that means, what does this mean? This means that the Laplacian operator, this is 1 by a square del 2 by del theta square in polar coordinates where r equal to a, which is a constant. In polar coordinates, if we keep the radial coordinate r as a constant, then the Laplacian operator is equal to 1 by a square del 2 by del theta square. Laplacian operators in Cartesian coordinates in Cartesian coordinates del 2f by del x square plus del 2f by del y square. This is Cartesian coordinates in 2 dimensions. This is the expression for Laplacian of f in Cartesian coordinates in two dimensions. In the same number of dimensions, in 2 dimensions, if I want to express the Laplacian operator in polar coordinates for constant r, this is the expression. Laplacian operators a polar form in terms of polar coordinates express the vi, in terms of Cartesian coordinates express the vi. Cartesian coordinates express organa siga manare, polar coordinates express organa siga manare. This is a special case. This is a special case where we have taken R to be a constant. R constant if we had not taken R as a constant, then we will have an extra term here. Extra term of derivative with respect to R. Here we have taken the special case where R is a constant for simplicity. We have some around 3 minutes. We can look at one theorem. So that a theorem what do Laplacian operator do this particular example, and what have we obtained? We have obtained the final answer as this. There is a theorem called Euler's theorem that is extremely useful in thermodynamics and a number of other fields. Euler's theorem have a theorem discussed. First, let us define a homogeneous function. Homogeneous function has defined. So a homogeneous function of degree p. Annotation a homogeneous function of degree p. It is a function. It is this function which has this property. Function variable x1, x2, x3 till xn. All these independent variables in J. So lambda multiply it is equal to lambda to the power p times the function of x1, x2, and till xn. For example, let us consider this example where f of xyz is equal to x squared z plus yz square plus xyz. Okay, let us consider this example. Let me stop the screen sharing.